and let's just start from that. And then after that, Alex, you will put together all the Q&A questions, right? For Gary to answer later on, please.
Yes,
okay.
yes.
Okay, and you will be posting it on LinkedIn as well, right?
Correct.
Okay, thank you so much. Okay, let's get started with Gary took the time to come over, make this presentation. Thank you so much, Gary, for that. And today we have an interesting presentation, which is produced water, transforming a costly waste products into valuable recycled components. Mr. Gary is the founder of the GAZ Water Technologies and is the managing attorney for GAZ Law Group with over 20 years of legal and technical experience. His intellectual property experience is focused primarily in the areas of US and foreign applications for patent, including applications relating to oil exploration, petroleum engineering, offshore technology, mechanical, chemical, refining technology, and computer technology. In 2000, he joined ExxonMobil as a patent attorney for the Upstream Research Company. At the Upstream Research Company, he drafted and prosecuted a worldwide patent docket for several divisions and Imperial Oil of Canada. Imperial Oil is, in fact, ExxonMobil. In Canada, it is functioning as Imperial Oil in the oil sands sector, primarily. In 2005, Gary was transferred to downstream research and engineering at ExxonMobil and focused on refining and finished chemical products, primarily drafting and prosecuting patents worldwide. Since 2010, Gary has represented major corporations, private clients, and startup companies with intellectual property, financing, transactional work, and litigation services with small, medium, and large firms. Gary has a BS in geological sciences and a JD, Doctor of Jurisprudence from Rutgers University. He's married and has a daughter and 4 sons. And you can reach him. He has got an email address, gary@gazwater.com. So with no more, I'm not going to add any more thing to it. I would like to invite Gary to go ahead and start his presentation, please.
Okay. Thank you, Salim, for the excellent introduction, and thank you to Carlos for hosting this event and for all his work. So I thought about the presentation. I was asked to present on the startup, and particularly the topic, how do we transform produced water, which we all know is a costly and problematic waste product, into a valuable asset. And not only do I, in order to have the group get the most value out of this, I'm thinking about telling it as a story so that hopefully people can learn from it as much as possible and gain from that. And I think it could be valuable because in today's environment, a lot of people are transitioning to entrepreneurial pursuits, whereas in the past, most people stuck with once you chose a corporate route, you were expected to keep the corporate route your entire career. Times have changed where entrepreneurialism is happening throughout in any stage of the career. It's not just young college kids or college dropouts, but it's people throughout their entire spectrum of the career. So I think by telling this as a story, my hope, at least my hope is that the group can learn as much as possible. And my name is, as Salim mentioned, Gary Katz. My background is in technology with ExxonMobil, and then quite a number of IP laws, quite a number of law firms. And I've had the experience of working for large corporations, medium-sized companies, and even startups, including now my own startup. So I've seen technology development in-house in a large corporation. I've seen it as an outside attorney, uh, and I've also now experienced as a startup. So hopefully, I can impart some knowledge to this group, and I appreciate the time. So what I wanted to do is lay out the the presentation. Now, whenever you try and start a business, you always have to start with the problem, because in order for a customer to give you the money, whether it's a service or a good, you have to solve a problem that's worth it for them. And then you got to make sure your solution solves the problem, and then the fit for the solution to the problem is your value proposition. Now, a lot of people start with the technology, and we always have to make sure that the technology is designed to solve a problem. We can never get the problem to fit the technology. So that's one of the most important things as an entrepreneur, is to fall in love with your customer and your customer's problem, because then the customer will be willing to pay for your product or service, not fall in love with your technology. And that's something I always have to constantly remind myself. And that's the key to being a successful entrepreneur, particularly for engineers that are very good with technology. And it's easy to fall in love with technology, particularly technology that you developed. Another aspect we'll go into the prototype testing and results, and then go a little bit into the business side, the customer segments, the competitions, our achievement, and then future pilot plants that we're proposing, and other considerations if we have time. So why did I start this effort? When I originally came up with the idea, water was very important. And as you can see in that map, Texas was in one of the worst droughts ever, and oil and gas at the time was booming, and we simply didn't have enough water for all the operations, and that included fresh water for operations, and as well as the disposal water, which is typically disposed of at disposal well. And oil and gas was receiving quite a bit of bad PR, because they were competing with farmers and ranchers, and often farmers and ranchers couldn't farm and ranch because the oil and gas industry was using all the available water sources. Now, a lot of times the farmers and ranchers figured out that they can make more money selling the water than they can farming or ranching, but it was still a bad PR. And of course, typically the media doesn't always tell the full story. So what are some of the customer problems? We always mention that whenever you want to start a business, you have to solve a problem, and solve a significant problem that the customer is willing to pay for it. So the problems that we were looking at were with the water, the infrastructure and cost issues. Also, there's a huge gas flaring problem, and until recently there was no solution to it. The gas flaring problem is still there, but becoming less because we're drilling less. But if oil and gas ever picks up again, we know that the gas flaring problem is going to come back. And even though it's not as great as it used to be, it's still out there, and it's considered wasteful. We also have disposal wells. They're hitting utilization limits. As these disposal wells pressure up, we're having seismicity concerns. We also have freshwater stresses. We know a lot of these basins are in areas with stress water. And everyone knows that in this industry, new regulations are constant, and everyone in the industry is expecting new regulations on water management. So to basically understand the water management cost and how significant it is, in Texas, it represents 55% of the operating costs for a production well site. So that's the average well site in Texas. They spend 55% sourcing water and disposing it. And as you can see, it mentions the acquisition. The biggest component typically is the transportation, where you put the water in a pipeline or a water truck, and then the next biggest is the disposal. So, freshwater acquisition, if you don't have a source of fresh water on site, typically they're put into large diesel water trucks and sent to the site. Now, more and more the industry is moving towards brackish, brine, and produced water, but there are some operations where you still need fresh water, such as if you're cutting the density of drilling muds or drilling fluids, and also some completions. Now, this is a map that shows freshwater scarcity and the degree in the U.S. And believe it or not, U.S. is one of the better countries as far as scarcity, but you can still see that we have scarcity issues throughout the United States. And very often, the major petroleum bases, the oil and gas bases, are located in areas that are suffering from severe water stresses. So anytime you're taking water in these areas for operations, that means there's a PR and a political concern because there's that much less water for other uses. I briefly mentioned the disposal. This is what a disposal well looks like. It's basically large water tanks where it's injected into a deep well under pressure, and the water is either fed by large diesel trucks like you can see in the bottom right, or pipelines leading into what they call gathering stations. Now this is a chart that shows the disposal well utilization limits. Now you can only pressure these formations so much before you run into serious issues, and typically the permits have volume and pressure issues, and more the disposal wells were hitting pressure utilization limits where they couldn't even put in the volumes that they used to because it was overpressurized. So this was both a permit problem, and the problem was expected to get worse. It'll be interesting to see with the cutback of drilling if this problem's going away or it's going to continue. But even if the problem is reduced because of the reduction in production, we would once production increases, we'll see the same problem come back. Another area that's received quite a bit of media attention are the seismic concerns. And as you can see, this map shows quite a bit of increase in the last since 2000, between 2019 over 2015 in seismic activity over the past nearly 20, almost 30 years, and including Oklahoma, where they had several significant earthquakes that have caused problems. And in Texas, we haven't had any major earthquakes, but we are seeing an increase of earthquakes, and it's directly correlated to pressure increases and pressure swings of disposal of water deeply, particularly if there's an aquifer. And what we're discovering, particularly if there's a fracture near the disposal well, and what we're discovering is very often it doesn't even have to be near a disposal well, because the pressure, depending on the formation type, can transfer over long periods of time, over long distances. Now, this is an interesting website, and this shows the increase. Texas and the Railroad Commission paid the University of Texas to put in a very sophisticated seismic monitoring system throughout Texas to understand the problem. And the University of Texas has been noticing quite a number of increased earthquakes over time. And so far, there hasn't been any significant property damage from these earthquakes. But the concern is that over time, these earthquakes are going to become increasingly intense, like they did in Oklahoma. And in fact, Oklahoma had to severely cut back disposal wells, which seemed to help solve the problem. So the fear in the industry is if there's a major earthquake, there's going to be significant regulations, and there might even be regulations without a significant earthquake. And then you also have the water infrastructure constraints. Massive pipelines are being built. Some of these are hundreds of $1 million projects to move the water, both fresh water and the contaminated water, to disposal sites. And a lot of times these pipelines simply ran out of capacity. And as disposal wells were reaching pressure and volume, this had to be piped further and further. In fact, in New Mexico, where water is a significant, much more of a significant issue, there was even a proposal to build a multi-billion-dollar pipeline system where water was taken from West Texas to New Mexico for the area of the Permian that was in New Mexico. And because New Mexico is much stricter on disposal and much more difficult to get permits, they were going to take the produced water back into Texas for re-injection. And then finally, the other problem is gas flaring. Billions of dollars every year in the US and other countries is being wasted in gas flaring simply because there's no pipelines, or sometimes even when there's a pipeline, there's no market for the gas. In fact, Texas Railroad Commission had recently had to issue gas flaring permits even when there was capacity in the pipeline, because the pipelines were charging to take the gas, and the producers said that if they had to pay the pipeline to take the gas, that the oil field would become uneconomical. So in a 2-1 decision, the Railroad Commission ruled, very controversial, that you can flare for economic reasons. There's a concern that depending on who wins the White House race, that there would be stricter regulations on flaring. And this shows the massive increase in flaring. I need to update this because recently flaring has gone down with the production, but it's still a significant problem. Now this slide basically shows how the water handling and disposal market is handled. So basically you have your water acquisition, which includes both fresh water, brine, and salt water, and that's usually mixed for fracking, but it's also mixed for drilling. And then the fracking fluid is injected. Now, probably most people here understand that, but there's 2 types of water streams. One is the fracking, which the water is injected in very high pressure to frack the rock in the hydrocarbon zones to allow increased permeability to allow flowing. Now, anywhere between 30 to 70% of the water injected as frack water comes back and is put in these trucks, and that's called flowback water. Now, for whatever reason, fracking receives 100% of the media attention. However, fracking is, depending on which basin you're in, 5 to 10% of the water management issue. So almost everyone is focusing on fracking, and there are companies that are already recycling the frack water. Typically what they do, or the flowback water that comes back, typically they'll take flowback water, produced water, and they'll filter it to remove the suspended solids and to kill the microbes, which if not treated will cause organic fouling through a microbial explosion. They oxidize it, typically using chlorine dioxide, which is very cheap and very effective, sometimes ozone. And then that water could be reused. However, this recycled water requires a tremendous amount of chemicals, and the service companies, Halliburton, Schlumberger, they make a tremendous amount of money selling these chemical packs to reduce the influences of a lot of these chemicals that are in this heavily contaminated recycled water. Now, The industry generally prefers to frack with fresh water. However, they're moving to recycle produced water and flowback water because they have no other choice, and it's just too expensive very often to use fresh water and dispose of the flowback water. Now, one of the things to keep in mind that even if we go to 100% frac water, which we can't because there's some frac jobs that require fresh water, it's not going to solve the production water problem because it's 5 to 10% of the problem. Approximately 90% of the problem is, if you go over to the top right, is when you're producing oil and gas, you have what's called production water. And typically that water is separated out of the well site through a three-phase separator, which separates the fluids being produced from the wellhead into three main components: your oils, your gas, which is then flared or treated and put into a pipeline, and then your water. Now, to give you an idea of the significance of the problem, in Texas, on average, for every barrel of oil produced, we're producing 8 barrels of water. And that heavily contaminated water is very often put into a pipeline. You can see the pipeline, or put in a disposal truck and sent to a water truck, which are diesel, typically 18-wheeler Mack trucks, and sent to a disposal site. And it's very expensive, and there's environmental concerns with destroying the aquifer, as well as also societal concerns that these trucks, and particularly in rural areas, are causing traffic. They're eating up, they're ripping apart roadways. So anything we could reduce this has both a societal and environmental and an economical benefit. So we mentioned that in order to have a successful business, you have to minimize or reduce pain points. And the problem is so vast, no one's going to solve this problem. So we have to minimize it. So what our solution is to take the gas, which is very often very cheap because there's a glut of it in the U.S. Even the Henry Hub price is very low. And speaking to most of the gas producers, there's very little value in this gas, and very few are getting even the Henry Hub price, which is historically low. And some are still having to pay the pipelines to take the gas. So either take very cheap energy or gas that's being flaring and use it to purify the produced water. And the goal is to reduce or eliminate as much as possible the pipelines, the disposal trucks, and the disposal wells. So what we want to do is take the gas, produce water, purify the water. You can get the water for on-site use, or you use it for agricultural, give it to farmers or sell it to farmers so that there could be more farming and ranching in areas in water scarcity. And the discharge brine we could actually reuse as a drilling and completion fluid by controlling the density. So eventually creating a new on-site business model. So the cost of disposing this production water is probably all over the map. If you're lucky and you have an on-site disposal well, the cost could be anywhere from 30 to 60 cents a barrel. If you have to pipe it, it could be anywhere from 10 cents to 50 cents a barrel to pipe it. If you have to send it by a water truck, the cost is actually $1 and up. So the moment a water truck shows up, you know that the transportation cost is minimum of $1. And in fact, in certain basins like the Marcellus, which is a very important gas production region, and condensate, gas condensate, liquid condensate, they have to pay between $4 and $8 a barrel. So, and the reason why is Pennsylvania banned all disposal wells, so there's only a handful that are grandfathered in. So the water has to be trucked from the Marcellus in Pennsylvania all the way to Ohio for disposal. So it really depends on where you are. So in Texas, which we're targeting, we figured a sweet spot would be between 50 cents to $1 a barrel, and we would target the well sites that have to bring in a well truck, a water truck, because then we know that the cost is well over $1, typically $1.30, $1.50 or above. So then, if we could charge them to take the water off their hands, we could charge them between 50 cents to $1 and have a significant value proposition to them in reducing their disposal costs. So once we get the oil companies to pay us to take the water rather than them being responsible for disposing it, we run it through a pretreatment system, which will remove the hydrocarbons and any of the iron and other potentially harmful metals. And then we run it through our purification system. And I'll explain the technology a little bit more. But we get, it's a thermal distillation system. We get a purified vapor and a heavy brine. Now that heavy brine can be sold as a drilling completion, a drilling fluid, a drilling mud, a 10-pound drilling mud, and a completion fluid by controlling the density. Now, believe it or not, that brine is very expensive on site, depending on the quality and the density. They can pay anywhere from $2 to $12 a barrel. One of the things is typically, at least in the Permian, very often the production sites are also close to the drilling sites, so that could be reused. Right now, with limited drilling, it might be harder, but to sell it. But there still could be a market, particularly if they don't have to transport it in. Now, the purified water can be on-site reuse, industry processed water, or agricultural. Now, the going rate for fresh water in Texas is anywhere from 25 cents. Actually, in areas of drought in West Texas, it could be as high as $1.50. In New Mexico, there's examples where people are having to pay $2 to $3 a barrel for water. Part of it is scarcity. Part of it is that, unlike Texas, where private landowners own the water rights, in New Mexico, the state controls the water rights, and it has to deal with the difference in laws. Texas has adopted the English common law, where the landowner owns all the subsurface aquifer water rights. And as far as surface water, whoever first takes the water for beneficial use gets it. It's called first in time, first in right. New Mexico is based on Spanish civil law, which is based on the Napoleon Code, and before that, Roman law. And under civil law, that is the state controls all water, both surface water and aquifer water. So anytime the state controls it, it's much harder to get it. Whereas in Texas, because almost all water is owned by private citizens or private entities, as long as you're willing to pay enough, you can get the water. And then we're also looking at metal recycling from both the pre-treatment and pulling out valuable metals from the brine discharge, and we'll explain that later. So essentially, what we want to do is create a new circular economy where every component becomes a valuable item rather than costly. So we all know that industry must become more efficient, and no longer can we waste products. We have to recycle them and do it economically. So we have a great team. I brought in quite a lot of people. Jerry's been advising me. I think he's on the call. Paul Smith, many of you know him. He was formerly with Weatherford. He's our chief product engineer. Ramesh and Antonio. A lot of people have helped me. Initially, when I had absolutely no money, I was bootstrapping. I couldn't even convince friends and family. And they did it for experience, and I'm very appreciative. And this is one of the things that I would point out is that quite a number of people helped me out in this entrepreneur's group. Not everyone I was able to reimburse, but several people who I never paid were actually able to use me as a reference and get jobs. So sometimes, and then several people on the team right now were helping me out and even volunteering the time, and now I'm paying them through grants and money from funds and money that we've raised for the startup. So what is our technical solution? So as you can see, this is our first generation prototype. And what we invented and patented and developed was a new thermal distillation system. So if anyone who understands thermal distillation, or at least the process that we use today, it's a very complicated process, and there's large chemical plants that have to perform this. So the basic technology is you have your energy source, could be gas or electricity, which produces your heat. You have your heat exchanger, which transfers the heat. You have your distillation column, where you separate where the water is distilled. You have your separation device, and you have your condensation, where the pure vapor is then recondensed. And I was reading a report by a professor who's trying to run a thermal distillation plant to purify water, freshwater quality. And I was shocked at how complicated this was, because this was such a simple technology. Let's face it, thermal distillation has been around since the beginning of technology. Why do they have to make it so difficult? And reading the report, the professor stated that it was very costly to run, and it was also very difficult to get each one of these equipment and process steps to work in a coordinated manner, as well as you had to run the pumps and energy source for each one of them. So I tried to look at the schematics of what they were doing, and I said there's got to be a simpler way. And I thought, why not integrate the gas burner with the heat exchanger? And you can see we have a gas burner on the bottom. We have a standard industrial fin tube heat exchanger on the very right, and then inside the heat exchanger you could put a distillation column, which is basically a tube. And what we did is, in this case, we gave it, instead of the traditional single flow path and closed system, we've opened it up and we've given it multiple flow paths through holes in the distillation column and multiple exits, so that gravity and density, gravity will allow the density difference between the pure vapor and the heavy contaminants to separate out. And then you have your pure vapor leaving one end and your heavy brine leaving another. And then we can for condensation, we can attach a pre-warmer, put a heat exchanger, so that not only do we condensate it, but we also recapture energy and make the process more efficient. And we built our first prototype, and before we built it, we had to run simulations. Here you can see a ANSYS fluent simulation, in which we saw how effectively the heat will be transferred from the combustion chamber to the fin tubes. Now, to simplify it, we had to show each step separately, and here you can see the transfer of the heat energy to the water flowing down. And what the simulation showed is that we could, as long as we get it to over 1,000 degrees Fahrenheit, we can achieve the majority of the water can be converted to vapor. Now, the prototypes, these simulations are very important. In fact, I'm looking for a ANSYS Fluent simulator in the future, going forward. And Carlos is working with me to help us find a candidate. So if you know anyone that that's experienced in ANSYS Fluent, and particularly if they have a recent PhD, we can get them in through a very great NSF postdoc program. But if not, I'd still be willing to talk to them. And that can do multi-phase flow, both liquid and vapor, which is very difficult, but very valuable for what we're doing. So I'd like to thank Carlos, and this is how a network can help. Carlos is starting with others a company to help connect, help companies find talent, and we're working with him. So, like Carlos says, you want to have as much networking as possible. So here you can see our prototyping testing. This is our first generation, very simple device. You can see the scale, very small. We were testing it in both Paul's garage and my garage, and we were powering it with propane gas. Now we're running it on natural gas or compressed natural gas, and condensing it into a bucket. We don't even have the pre-warmers. And with this small little device, we were able to remove over 98, now we're over 99% of contaminants in a single pass-through of under 10 seconds. And what is really unique about this is there's no mechanical moving parts. It's gravity fed. So the only thing that will cause a failure is corrosion, fouling, or scaling. And because it's a short residence time of under 10, now we do it under 12 because we're using slightly bigger equipment. There's not enough time for scale and corrosion to form, which is very promising. You can see our lab results. Now, once we did is we took this lab results, and initially I applied for NSF funding. I tried to get investors behind me. No one believed it. Once we actually bootstrapped and were able to build a prototype, I had to beg a family friend to lend us some money to do this. We were able to send this to the NSF, and they gave us phase 1 funding so that we could build better and bigger systems and field test it. So as part of our NSF SBIR phase 1 funding, we took it to the field, and this is the first generation. We actually took a second generation there, and this is actually a well site in Spring, Texas. You could see the frac tanks, and behind that are the gun barrels where to produce water. The center is the wellhead. To the right is your glycol gas processing. Bottom left, you can see the pumper talking to our team, explaining to us. While we were there, a water truck showed up, and we were able to talk to the water truck, and he gave us some very valuable information. That same truck also delivers to well sites both fresh water and brine. He even knew a little bit about the pricing structure, which confirmed to us that if we were able to produce fresh water and brine on site, instead of having that truck having to pay that truck to take the disposal water, that truck can then be a profit or revenue generating to taking fresh water and heavy brine to other sites. So this is what we're in the process of building our first commercial unit. We started this at the end of our phase 1, and we're using phase 2 commercialization money, grant money. And I think 2 years ago when I started this process, gave a talk on grant funding. I'd be happy to give another talk on grant funding and how to find it, apply, and draft the grants and the whole entire process. So this is all inside our trailer, and we're planning to scale up by adding additional units. As you can see in that skid, which we would put in a trailer, we could fit up to 12 of these, and the goal is to eventually get over 1,200 barrels per day. And right now, our biggest issue is increasing the volume, and we're going to do that by improvements in the design, as well as running it more and more in parallel. And this is as you can see, we have a SCADA system so that we can run it remotely, so we don't have to have a team there on site 24/7. So basically, you can see the evolution of the technology from simple modified heat exchanger to actually a system to putting it inside a trailer to be able to run it on site by simply connecting to the water line and gas lines. So we're proposing some field trials, some larger ones with major and an independent that's probably just below major. And so we're doing schematics of how to do it. This would be at the water gathering stations where they're re-injecting, where we attach our system and then have the trucks to take the brine and the water to the different storage tanks or to the end users. Now, one of the most important things we had to do throughout the process is customer discovery. And we worked with several different organizations. Probably the best one was what's called the NSF I-Core program. And they have different versions of it. The main one is a regional program and a national program. And the regional program is run by, there's a regional node where several of the universities are running it. University of Texas, Texas A&M, and Rice are among them. And they have different free events, courses you could apply. It's a simple Google document. It takes about 20 minutes to apply, and as long as you have a reasonable business model, they'll accept you. And you just have to show up at the courses. There used to be 2 of them were in person and 2 of them were online. I think because of Corona, they all go online. And what they wanted you to do was to do a series of interviews, and you couldn't discuss your technology. Why? Because they've adopted the lean startup model. And the lean startup model is all about solving a problem and constantly pivoting until you have a business, either a service or a good, that solves a model, that solves a significant problem that a customer would be willing to pay for. And what's interesting about this lean startup approach is when you're talking to a customer, at least initially, they don't want you to sell to them or talk about your technology. Why? Because if you're selling to them or talking about your technology, you're not understanding your customer. You're trying to get the customer to understand your product. And the customer will then be biased very often, whether they like you or not, whether they like the product. So what the I-Core process, or the lean startup model, which is adopted by Stanford and other business schools, is that when you're talking to customers, you ask them what their problems are with open-ended questions. And then through a series of questions, you could very quickly tell whether or not your proposed technology or solution will solve the problem. Now, to give you an example, now the regional one was, I think, 30 interviews. And then if the instructors like you, they propose for a national program, which is also considered a phase 0 grant, in which the NSF will give you and your team, you have to have 2 or more people, $50,000 to cover travel costs, but you have to sign a commitment to do a minimum of 100 interviews during that process. So we did both, and both are excellent programs. I highly encourage everyone. So one of the initial things we learned is when we developed this new distillation process, I thought, all right, I'll build equipment and I'll sell it to the producers. Tell them, look, we can purify the water. You can get the fresh water. We weren't sure about the brine reusing it, but we figured they could significantly reduce their disposal costs and reuse and fresh water acquisition. They'll buy the equipment. Well, initially I probably spoke to at least 50 customers, and then I gave up. Not one customer would buy equipment. Not one. And I've spoken to the small family offices, to the service companies, to the mid-sized producers, to the largest majors in the world. And they all looked at water as an operational cost, and not one would consider ever transferring it into a capital expense. So we had to pivot and realize we actually have to provide a service because they have a significant problem, but they're paying to make that problem go away. And right now, they don't want ownership of that problem or any more headaches by running equipment. They want that problem to go away for less money and less environmental and PR costs and logistical costs than they have today. So we had to transition to a service model in which we take the water from them on site and then we handle. And looking at the numbers, actually, even though it complicates things, it actually presents potentially a much more lucrative business proposition. We also signed up for Clean Tech Open, which is an accelerator program. And then as part of our NSF Phase Zero grant, we did a pilot program where we enrolled into the Austin Technology Incubator. That's in Austin, and that's affiliated with UT. And then we also work with Shell, NREL, and the Small Business Development Centers. And there's several of them. There's one in Houston, there's one in San Antonio, there's one in Austin. And if you're starting a business, they've been extremely helpful. So part of a business is to figure out your customer segments. Now, to give you an idea of the scale of the problem, in the US, the operators and well site owners, they spend $37 billion a year. The number might be going down because of the reduction of oil, but still a very high number, on water management, acquisition, and disposal. Now, of that 37 billion, 20 billion are what is called the water midstream companies. These are the companies that bring the water, transport it, and dispose of it. So examples are WaterBridge and Solaris. The on-site providers that provide water on site and treatment services is approximately 9.7. Now, a completely different segment, and I'm sure this number has gone down significantly, drilling salt, which is the base stock for most muds used in drilling. Offshore, they use generally more either crude oil or synthetic oil as a base stock, but almost all drilling in onshore now is salt, and that's the drilling salt providers is a $6 billion industry. So very significant segments. So what is our competition? Whenever you're talking to grants or others, you always have to know your competition. Honestly, our competition are the disposal wells and the midstream companies that are putting in a truck or a pipeline and re-injecting it. Now, surprisingly, even though initially we looked at it as competition, these midstream companies are very interested in working with us because they know that long term, it's not the current practice is not sustainable. So even though they're probably our biggest competition, because that's how 99% of the produced water that's not being recycled for frac water is being handled. Now, as far as technology, Veolia has a thermal distillation plant. You can see it's a massive chemical plant like I described before. And Gradient came up with a humidification, dehumidification. Again, a very expensive, massive plant that you can see on the bottom right. So we had to do a comparison, not just against what it costs to put it in a pipeline or a truck and dispose of it, cost-wise, but people asked about what about other technologies, particularly grant and investors. So we compared ourselves to Veolia. Now, that trailer, which could do about 1,000 barrels per day, versus Veolia, which could do max 24, you could see significant savings in capital costs, energy costs, because we're using cheap natural gas, even paying Henry Hub the retail price. We save money over the operating costs, and that's using 24/7 manned personnel, where we can even go cheaper. The water sales from the fresh water, our system, we're able to resell the brine Veolia you can't, so you have to dispose of it, and you can see the physical footprint. So in every way, a a um, a superior technology to what's commercially available. Now, one of the things that I've learned is, even though Viola might be the closest technology out there, we're not competing against Viola. And the reason why we're not competing, they're just too expensive to anyone use. So, if you want to hear something funny, I haven't sold a single. I've actually made $2 so far because I did a field trial where the NSF asked me to have the customer pay for it. So they paid me $1 a barrel for the water that we evaporated. So we've made $2. Viola is the largest water company. Because Occidental is considering using our system and won't even talk to Viola about their system, I was actually banned from their industry day. So I'm probably the only one. They invite the entire water spectrum, and I've been banned. So it just shows that thinking outside the box can scare even the largest companies in the world with the bootstrap technology that was developed in a garage. Now, even though Viola considers us competition, I know better, we're not, because no one's even remotely considering using them. So our competition really is the disposal wells and the midstream companies. So IP, it's very important because once you prove a technology, if you don't protect it, so we filed patents. We have 3 issued. We actually have 3, instead of 2 out, it's now 3. We have filed 13. That should be 15. We filed 2 more. We've trademarked some of our names, copyright, and then even trade secrets are important. So our algorithms, our operating data is very important. So if someone wants to see that, we require them to sign an NDA. So what's our go-to-market strategy? Now, I am talking to some of the biggest companies in the world about doing a large pilot plant, but really, right now we're funded with an NSF grant. It's just enough to get by. We also borrowed some money from investors. But really our commercial pathway is to go to the small family-owned offices, like the family that owns that small production site in Spring, Texas. And that's typically less than 1,000 barrels a day. At that site, it's about 100 barrels a day. And you can see the test samples from that site where you have the produced water. We concentrate it to heavy brine, and you can see the condensed vapor, which is fresh water quality. So that water was approximately 150,000 TDS. We condensed the brine to right around the 10-pound drilling mud, which is around 260. And the vapor is under, the purified water is under 500 TDS, which is actually fresh water drinking quality. But EPA regs will not allow us in the US. Maybe in other countries, this would be better drinking water quality and could be used as drinking water. So we had to do revenue and show that we had for investors, a profitable margin. But because we could take a costly water product and recycle it into valuable components, you could see we have the potential by adding 12 wells a year and then doubling it. These are very small wells of under 1,000 barrels per day and have a very sustainable revenue model in there. Based on our market research, there's approximately 8,000 wells that initially we could target. So this is our timeline. I know I'm running out of time. So you could see last year and this year we were funded through an NSF grant that's going to run through 2021, in which case we're going to have to transfer to commercial funding and commercial improvements. So I'll go quickly over our proposed field trial. This is a larger one. So we had to show a process flow diagram of how we'd fit on the well site. And basically we took the standard well site and added our red desalinization unit. And all we had to do is add either a fresh water tank or pit and a heavy brine tank. and we could integrate into most well sites the existing systems. We had to do an OPEX to show that even on a large scale it could be profitable. CAPEX, we can explain it later. Here we have a site placement and flow diagram for 10,000 barrels per day. And this is a rendering of our XFAP thermal distillation system in a shipping container to show what it looked like on site so we could scale up by putting additional shipping containers. We're not here yet, but our goal is to get there in 2021. So considerations with working with these companies, confidentiality. Some companies want absolute confidentiality, some don't want. The cooperation structure. Are we doing this as a as a research project? Are we doing this as a consultant, a contractor? Publicity. Some want publicity, some don't. And inviting other parties. Benefit will be cost sharing. Some companies are willing to work with others. Some want us only to work with them. So those are all considerations. We're working with investors. There's matching funds as far as our NSF grant, and we've also taken some loans. Another interesting component that we're working on is people are looking at extracting valuable metals and minerals. We've talked to Pure Lucid, which can extract lithium if it's in greater than trace amounts from the produced water using their technology, and we could do a license agreement with them. More interesting technology is I'm working with a company called New Arrow, and they were a technology spinoff from Statoil, and they have a microbial process where initially they injected microbes. Now they're injecting nutrients and causing a microbial explosion of microbes that can repel water but will allow hydrocarbons through. So for an EOR situation, it's very valuable because it increases the hydrocarbon recovery rate while reducing the water. So we're actually now working with them, and we filed several patents on this, on using microbes to selectively remove valuable metals and minerals. And we found microbes for just about every critical material out there, including the ones that they're scrambling to find domestic supply because most of it is coming from China. Lithium, nickel, cobalt for batteries, and rare earth elements for the high tech. So for the safety concerns, we had to do this for one of our majors, show all the safety considerations, ESG, the sustainability benefits. Now sustainability has three components. You have your economic, which are the benefits, which is reducing costs and recycling. Your environmental, which is reducing freshwater withdrawals, reducing seismicity, and also the vehicle miles traveled emissions. These are heavy diesel trucks producing considerable CO2 with the runs on the water trucks. And the societal benefits. So we want to reduce the depletion, use less fresh water for oil and gas, and then reduce road congestions. And by reducing the cost for the producers, we're making energy cheaper for everyone, and that's a net benefit because when energy costs rise, the ones that are hurt most by it are the poor and middle class. So all these are benefits to society. We talked about the emissions, natural gas as one of the lowest emissions, and we're even working on a carbon capture. Since we're going to be at the well site and burning the gas in a controlled manner, we can re-eject the CO2 we produced on site. So we have a number of achievements, and I think I'm out of time. I was supposed to talk between 9 and 10, so that's been an hour. I'll be happy to take any questions.
Gary, you have time, so there's nothing to rush. If you have other things to show, to present, by all means, go ahead, please.
Why don't I take questions because I presented for an hour, and
Okay.
I could talk more about the metals and mineral recovery. I could also talk about some other technologies, spin-offs we're looking at, such as solar desalination. But figured I've talked for an hour and would, love to get questions or feedback if people want to discuss solar desalination or the metals and mineral recovery. I'd be happy to do that too.
Okay, thanks a lot. Thanks for your presentation. Alex, do you want to go ahead
hello,
and do a Q&A session, please?
Yes, we got a few questions here. Our first one is from Celine. He states, what are the contaminants that you are separating?
Okay, so great question. Anyone who's a chemist in this group who's looked at produced water knows produced water has some of the ugliest chemistries you'll ever find. A lot of naturally occurring metals and minerals are dissolved in a lot of elements dissolved in the water, including arsenic, which at high levels can be toxic, but in low levels is naturally forming. So what we've discovered is we're removing now 99.6 of all TDS. When I say TDS, that's total dissolved solids, and it doesn't matter what type. And the only reason why we're not removing 100% is because of chemical property called entrainment. When you vaporize a fluid into a vapor, there's a significant amount of energy, and that vapor can carry a certain amount of solids with it, and when it gets recondensed. Now, if we wanted to get to 100% pure water, we could by adding multiple steps of the distillation process, or very easy putting in a vapor membrane that will allow the vapors through but not the solids. Now, the only thing we are not removing is the lighter aromatics. So if there's some aromatics or VOCs in the water, they typically have a lower flash or vaporization temperature than water. So we're getting some of that when we recondense. However, there's plenty of ways to deal with that, such as pre-treatment. We can oxidize it. We can let it sit and off-gas it. So if the VOCs are a problem, we'll have to deal with it. If not, generally speaking, there's a limit to discharge, and as long as we're not on the discharge, we're fine.
Thanks.
Okay, our next question here is from Subhash. What is the purpose of the glycol gas processing equipment? Do you take the acid gases out of the flared gas?
Okay, so the purpose of the glycol unit is to remove the water. So typically after the three-phase separator, where you get your oil, your gas, and your water. So your gas is your oil is either put into a pipeline or a oil truck and then sent to a refinery for further processing. Now your gas very rarely is considered pipeline quality. There's different types of gas. They call it sour gas if you have H2S, wet gas if you have water, dirty gas if there's other contaminants. So what they do is they have to run it through steps. So one of the first steps they do is they remove the water from the natural gas, and typically that's done in a glycol system, and that's designed to remove the water. After the water is removed, they actually run it through a Grace membrane system, and that removes the CO and any H2S that's in there. And that system is very sensitive to water, so they can't have any water in it. And then it's typically, the next step is it's pressurized and then sent into a pipeline. Now this site, they're very lucky. There's a Kinder Morgan interstate gas pipeline, so they're getting very close to the Henry Hub price.
Hey, Alex, is there a chance to follow up?
Sure.
With Gary? Yeah,
Yes, please go ahead.
Yeah.
Hey, Gary, I guess the question, this is Subhash. The question I was posing is, first is, when you use the distillation process, the thermal distillation process, is it taking energy or heat all from the waste heat, or do you actually have to supplement by burning additional natural gas or something else?
The answer is yes and yes. So if there's significant waste heat, we could take it. In fact, we talked about using the glycol system. I'm not sure there's enough in there to make it worth our while. In order to get it up, we'd still have to burn some gas. Another process we're talking at the wellhead, it's coming out extremely hot, sometimes very near distillation temperature. So we can run that through our energy recapture system and then use only a very small amount of gas in the process. So yes, almost always we'll have to burn some gas, but if we could recapture the waste energy on site, we could significantly reduce it. And in some areas, it could be possible to run it completely on waste heat energy.
Okay, and then the follow-up question was, if you have to burn additional natural gas, let's say, then you're creating this additional emissions like a CO2 and other products. Would you be required to trap that? Would you be required to sequester that or do something with it? Or how do you handle those emissions in that case?
So the answer is yes, burning gas creates emissions. However, we have a glut of gas, and a lot of that gas is being burned anyway. So if the gas is being flared, it's an emission problem already. If the gas is not being flared, then we've looked at it from a carbon footprint standpoint, and running the natural gas to purify the water, particularly with our energy recapture, is typically less than the emissions from a CO2 truck. Now, when we spoke to the Texas Railroad Commission, we will not need to get a permit for this because we're just burning gas for use on site. It's no different than running a gas generator on site. You don't need a permit for it. Now, if there's contaminants that are causing air problems, we might need a permit, but since most of the gas is treated on site, we could use the treated gas on site without having to get a permit.
Okay. Thank you.
Okay. So we can move on to our next. Yes.
Alex?
Yes.
Can you hear me?
Yes.
What I was thinking, can we just take a brief pause of this Q&A session and go to a picture session? Francisco will take a picture of all of us.
Okay.
Then we'll resume that Q&A session before we lose some of the people.
Okay, let's do that.
Okay, Francisco, go ahead, please.
Should we get a better picture on there for Gary?
Yes. Francisco, you decide how we're going to do it.
Yes. Okay, everybody, you can turn your video on. I want you smiling and looking happy because we just learned about a the way of the future to handle this produced water, correct, Gary?
You want me to shave so I look a little bit more presentable?
No, 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 no. I want you rough. That's
Okay,
good.
rough. Okay, you got it. I look pretty rough right now.
Okay, anybody else? Just comb your hair, ladies, and don't worry about it, you know. That's it, Kathy. You're doing real fine. Madhu, are you gonna show up or not? No, he's not. Jeffrey?
Mamdu, you are muted probably, right?
No, he's coming. All right, nice and pretty, Madhu. That's it. What about Jeffrey? Where he is? And Lee? Okay, we got almost everybody.
Margaret is there?
Yes, I am here.
And I need Lee.
We need some ladies there too.
Wow, okay. So, Lee, if you're not gonna show up, I give you 3 seconds. I'm gonna take a couple of pictures. Okay, so I guess Lee is not gonna show up. Okay.
Yeah, I can see the participants.
Uh,
Okay. One more. Okay, if you want to switch, you know, look a little. Oh yeah, hey, you got it, Alex. You got it. You got the idea.
Alex and Francisco, do you want take a picture of Gary with one of his nicest slides that he would like, so that when you do the posting on LinkedIn, it is there?
Well, what I can do, I can also get it from the recording.
Okay.
You know, capture it from there. So I guess Eric already took off. So I'm gonna take one more picture.
So we'll let Francisco pick. We'll see if he likes me or not. If he likes me, he'll pick the best one. If he doesn't, he'll pick the worst one.
That's it. That is it. Okay. So I'm taking picture number 2. Okie dokie. That's it. Now you can relax. 2 pictures taken. We can go back to Q&A if you want, Senator.
Thank you so much. Before we go back to Q&A, and before some of the people leave the session, I want to tell something more about Gary. Gary has been with us, with our Paid For network for some time, and he has made other presentations in the past. His other expertise, which probably will assist you in the long run, if you have to apply for National Science Foundation's grant, he can help you on that one. Besides, I think if you want to patent any technologies that you may be working on, he will probably be able to assist you on that one as well. So, and in the future, I'm expecting and hoping you may be able to come back to us, make a presentation on any of those 2 topics as well.
Okay.
Because he made a presentation on this topic earlier, on the other topics earlier probably, so I decided, he gave me an option. These are the presentations I have. I said, let's go with this produced water one. That's how he came to make the presentation today. Yes, okay. Gary, go ahead.
Show of hands, if I get invited back, would you rather have me talk on grant funding or on intellectual property? So all those for grant funding?
Mm-hmm. I am for grant funding and for both actually.
Okay. And then who would be interested on a talk on intellectual property for small businesses? Okay.
Question to Gary. Can you do both in one Friday, or is they're too long?
No, it's too long.
Too long. We'd have to split it up.
Let's just split it up. Yeah. So Gary, if we choose something after the election in November or first week of December, can you do it?
Yes. All right. And
okay.
Do you want to get with your team and figure out if the preference is grant funding or intellectual property.
Okay, we'll work on that one. Thanks a lot. I appreciate it. Alex, let's go back to Q&A. I think there are a lot of questions.
Okay.
Some of them have not been posted there, but for example, I have some other questions as well.
Okay. So let's go to our next one is for Eric Beam. This question is, how big is the market for the brine? What would it cost to get rid of the unsold brine?
So excellent question. The answer is, I'm not sure what the market is today. I'm sure it's significantly worse than the numbers I gave on that slide. So we'll have to find out when we start selling the brine. So hopefully the market will recover, but who knows? The answer to what's the cost, it's essentially the same, because disposal is basically a volume cost. So if we have to concentrate it down, the cost would be the same per volume, but because we're concentrating the brine, there'll be much less of it. So there'll still be a value proposition, but that's not our goal, obviously, because our goal is to maximize recovery and revenue and recycling. But if there's no market for the brine, you're right, it has to be disposed of, and the disposal is generally the same cost per barrel. They don't charge, almost all disposal wells charge a per barrel fee. Same thing, the water trucks hold so many barrels, and the pipelines charge a per barrel fee.
Okay, our next question here is from Scott Myers. He says, "Hello, Gary. How have you considered the potential applications for applications in the geothermal industry?"
Yes, and in fact, we were thinking about putting in a grant application because the DOE is promoting both solar energy and geothermal as alternative energy sources. So we've actually proposed a solar desalination system that we're working on, we were considering putting in a proposal for using the geothermal heat energy as a way to purify water. However, we just didn't have the resources and time to do everything. So the answer is yes, and hopefully we'll get the resources and time to be able to apply for funding and progress that technology, because I think there's tremendous opportunity there.
Excellent. Okay, our next question here is from Francisco. I might be a two-part question, but question one, can these units be rented to the owner of the produced water?
We could, and we were talking with one of the majors about that. However, they don't want to operate it. So even if we were to do something like that, we would have to have agreement that our team would be the operator. So it's just the perception of the industry, and we all know oil and gas is a very old and conservative industry, and it's hard to get people to think differently. Mm-hmm. So the industry views water as an operational expense. So even though renting would make it into an operational expense, they don't want the headache of having to hire and be responsible for crews. So they would rather someone take the water away, whether it's us, the pipeline, or the water truck, and once it leaves their site, it's no longer their problem.
Okay, and I'll just jump to question two from Francisco. Would the government in charge of monitoring the produced water can request produced water conversion to clean water to avowing transportation hazards?
Yes, in fact, the government is looking at that. Texas has actually a bill pending in the Texas legislature to actually provide a subsidy. It's actually quite controversial because anti-oil and gas people are saying that it's a handout to oil companies to subsidize their costs to purify the water rather than dispose of it, particularly the fresh water quality. However, some are saying, look, this is no different than wind and solar subsidies, which are necessary to create a new industry. We want to create a new industry of recycling and reusing this water. So initially, sometimes you need government subsidies. So I don't know what's going to happen because there's strong opinions, but one option is the government actually subsidize it. Another option is once technology is feasible without hurting the industry, the government could potentially regulate that you have to purify the water on site rather than dispose of it. Now, ironically, among the environmental groups, there is a wide variation in how they think. Most common sense environmentalists like the idea of purifying the water and recycling it because they know that we have a worldwide water problem, and as population increases and our freshwater resources diminish, we have to create new sources of freshwater, whether it's reverse osmosis desalination from seawater or others. For society to survive, we can no longer rely on existing natural sources of fresh water. We have to purify water. So there's a realization that one potential area for environmental improvement is to take contaminated water, instead of disposing of it, recycling it. And most are in favor of it. There are some extremists that just hate industry and they hate oil and gas. And they look at this as a way for industry and oil and gas to make more money. And they are spreading concerns that they're going to poison crops, they're going to poison the aquifer, and poison people. And it's just a way of thinking. And, they don't care that we can purify water, industrial wastewater, to better quality than than almost any municipal water available. And in fact, people tell me, well, what about arsenic and other contaminants that produce water? One, we remove it so we get it to safe levels. And two, I tell people that when I first started doing this process, I was using tap water from the city of Houston and Katy and Morton salt that we were buying from HEB. And when I took the water to an EPA lab, the Morton salt, the synthetic heavy brine, which composed of City of Houston tap water and Morton salt, had 9 times the EPA recommended limit for arsenic. So I tell these environmentalists that if you're really worried about contaminated water, talk to the City of Houston.
Don't forget to go vote.
Yeah. So, look, we have serious issues, both in industry and environmentalism, and we need to have common sense solutions. So hopefully, obviously what I'm proposing is not perfect, but we can't allow the desire to have a perfect solution to prevent the improved solution. And that's what we're proposing here, improved solution. And I believe the goal of industry, of government, and the environmental groups are to constantly improve, and over time we get better and better, and that's what we're here for constant and never-ending improvement, and that's our growth, and that's how we contribute to society. So hopefully, yes, we'll see more and more of this. I'm sorry if I gave my political view on this.
No, that's all right.
No, it's fine.
Our next question is from Morris. He asks, can seawater be used as an initial injection medium?
Yes, we can use seawater. However, at least right now, we've done the economics. We can't compete with reverse osmosis, even though we're cheaper than thermal distillation. And so we have to focus on the industrial water and heavier contaminated water. Now, RO can handle this type of water because the heavy salts and a lot of these metals will foul and destroy the membranes. So we're actually handling an area that RO can't. And I'm speaking to RO companies, and they're interested in combining the technology. Why? Not just because we can initially handle contaminants that RO can't, but also the way RO works is typically only economical at around 30 to 40,000 TDS or less, which includes seawater. However, once you get to 50,000, it destroys the membrane. So your theoretical limit is 50, maybe 60,000 TDS. So you can only concentrate the brine to a certain level using RO because it's going to destroy. So if they want to concentrate it for industrial reuse or to limit their disposal volume, they have to go to a thermal distillation. So there might be an area. And, we're even talking about over time, as we develop the technology and improve it, maybe we could become economically competitive with RO, but that's going to take some time because probably some of the greatest advancement in water treatment the last 20 years have been in the Middle East, where the cost to perform RO has drastically been decreased.
Okay. I don't know if Morris is still with us to follow up, but he's got another question here.
Sure.
What is a typical operating or max pressure of the disposal well? What are other methods of disposal if not in a well? And what are the environmental issues?
So basically, the only other, they've tried spraying it in the air and trying to evaporate it. The problem is, because of entrainment, it can take the contaminants into the air and cause problems with air pollution, and vegetation is known to die around it. So really almost all the water is handled through re-injection. If it's not reused, fracking, it's handled through re-injection. The only other technology, which the industry has been getting away from it, was what they were doing was these evaporation ponds. And what they were doing is they were lining these gigantic pits with a liner and pumping the water into extremely large ponds. And over time, the water would evaporate, leaving the salts. And then once they got enough salts, they would let all the water evaporate, and then they would dispose of the salts in landfills. Because of the enormous amount of land you need, it is generally not economical unless you have very small water amounts.
I don't know if there's a follow-up to that. I don't know if Morris is still with us, but let's move on to our our final question here is from Francisco. It says, Gary, with this invention, would you be hurting another industry?
Potentially. Ironically, the one industry we would be hurting the most would be the midstream oil companies. And when I meet with them at industry seminars before COVID, they were very interested in what we were doing, and also very interested in trying and adopting the technology, because one, they realize that what they're doing right now is unsustainable in the long run. They're seeing it's getting more and more difficult to get permits. It's becoming more and more expensive to operate these, and oil and gas companies are pushing back. So some of them that were having pressure issues at their disposal sites, I've even mentioned putting this on a disposal site and trying to still keep the volume of water that they used to take, and purifying some of it that their disposal wells can no longer handle. So yes, in theory, we would take money away from the water midstream companies, but I would say the interesting thing is the industry isn't looking at this as a zero-sum game. They're looking at it as, we have a serious problem. It's a huge problem. There's a need for multiple players, and even a technology like this can't completely eliminate the disposal problem, because there'll be some times where you have no choice but to dispose of it. So other than that one example where Veolia looked at us as taking business away from them, which was a ridiculous position, because I spoke to the company that they were upset that we were working with, and they weren't even considered their technology because it was too expensive. So why they were upset at me, I don't know. So we're not taking any business away from Veolia because they're just too expensive.
Well, Scott, isn't that renewable taking away business from fossil fuels or non-renewable? There's a big fight going on that as well, right? Scott, are you there?
Yeah, I don't know if Scott's there, but the one thing is we all know is this industry is constantly changing and constantly will change. So we have to be prepared for changes, and there's going to be winners and losers. The most important thing is to progress it, to provide the industry a value proposition, and also benefit society. So providing water, cutting the cost of disposing of water, making energy cheaper, those are all significant value propositions. And yes, we're going to move to alternative energy. I now saw a report that solar is the cheapest form of, solar and wind are cheaper than electricity from solar and wind are cheaper than hydrocarbons in most countries, and the price is probably going to go down. However, even still, with solar expected to take up 80% of the increase of energy consumption in the world, oil and gas is still going to be the predominant energy source, most projections for the next 30 to 50 years. So, I don't, it is a marketplace competition, but I think it's wrong to look at this as a zero-sum game. We need to look at this as whoever can provide the best solution is going to win.
That's right. Yeah, thanks. Well, I guess the questions that were posted in chat session, they're over, but I think we may have other questions. For example, I have a number of questions for you, Gary. Some of them are directly related to produced water. Others are not directly related, but they come from questions come up from your presentation. Can I start asking you a few questions here, please?
Sure.
I didn't quite understand your XVAP technology. Are you saying, I'm trying to understand it, are you saying that you are trying to heat the produced water and vaporize it And in doing that, you are taking out some of the valuable minerals and metals out of it. And whatever you vaporize, do you finally condense it and capture it? What do you do? I don't quite understand. Can you
So the
expand on that?
vapor is recaptured in in the condensing unit,
Okay.
and that's purified water, and the metals and minerals are taken off. So here you could see process flow diagram. We have your produced water. We run it through a pre-treatment, in this case electrical coagulation. Above it is the heat exchanger. Then we run it through our XVAP, and then we could take the brine and the metals removed from the electrical coagulation and perform both chemical and microbial processes to.
Hey Gary, can you use a pointer? Do you have a pointer available some way?
No, I don't. Being a tech startup, I should probably be high tech, but I'm not.
Yeah, that's causing me difficulty following what you're saying. You got to kind of point it.
I think
let me see if I can find a simpler diagram to show what we're doing.
Okay.
Does the cursor show on the screen?
Oh, you want me to use a cursor?
Yeah. Why don't you use the cursor, please?
Yeah, that's okay.
Okay,
That
so
would
let
be
me.
good.
I'm no longer looking at people, so if they want to, they can actually make faces at me.
No, that's fine. Don't worry.
Okay, so can everyone see the hand?
Yeah.
Yes.
Yes.
Okay, so as you can see right here, we have the XVAP thermal distillation system.
Mhm.
And what we do is the gas is coming in on the bottom. We have an air supply coming in here. We have the mixture of gas and air in a combustion chamber with the fin tube heat exchanger that transfers it. Now, in here, one of these is the produced water coming in, and the other one is a brine exit line, and the other one is a vapor. So the flue gas comes in here and it comes out this chimney. If we were to capture the CO2, we would have a capture system, maybe some type of almost like a catalytic converter to remove everything but the CO2 and then re-inject the CO2 in. These two devices, those are plate heat exchangers. Those are a pre-warmer. So one is for the brine and one is for the vapor. And the condensation occurs when we run it through the pre-warmer, where the feed coming in, the produced water coming in, is warmed through first the brine, then the vapor, and it's very hot, almost at a thermal distillation before it gets in the system. The system separates the vapor, which then goes to the heat exchanger and is condensed as it's pre-warming. And the brine, which is the heavy metal salts, is then also sent through a pre-warmer and then sent outside for storage. So you could see that. Now, if we were to recover it, we could recover it through the pre-treatment system, which is some of the valuable metals, which is not shown, such as electrical coagulation. And we can also recover it through the brine through microbial or chemical precipitation process. So did that help explain it?
Yes, it does. Thanks a lot. I appreciate it.
Okay. All right. Should I go back? If anyone's making a face, I'm now watching you, so.
Does anyone else have any other question? Otherwise, I want to pose to Gary my other questions.
Okay, go ahead. I have a question too, Salim.
Yeah, go ahead. Then let me give you a chance. Yeah.
Yeah.
No, Gary, I have a personal question. I want to have a phone conversation with you offline. What's the best time to call you?
Salim, can you email my phone number?
To Mamdou?
Yeah, Mamdou's email.
Yes, I can do it. Yeah, I think I suggested Mamdou to contact you. I think, is that one, Mamdou, you're talking about?
Yes, yes. I wanted to talk to him, but I wanted after the
I'll send
presentation.
you. I'll text
Yeah.
you later on his phone number. You can call
So,
him.
Great.
Mamdouh, today I'm very busy this afternoon. So, because I actually have a patent deadline. So what
Sure.
I would do is I would actually maybe email me on Monday, and we'll set up a time either Monday, Tuesday, or Wednesday. Okay?
Great. That sounds good. Thank you very much, Gary.
Okay, Subhash, go ahead with your question.
Okay, sure, yeah. So my next question was on the desalination, the slide that you have on the screen right now. So how does this setup that you're using right now, or you're thinking of using in the oil field, is that applicable to a large scale desalination project? And how effective or ineffective will that be?
Yes. So it could be over time, but if you remember, we talked about large scale. If we're doing a simple desalinization, such as a seawater,
Yep.
reverse osmosis is your better bet.
Mhm.
And IDE and others have so drastically reduced the cost. As far as seawater desalinization, it's going to be very difficult for this technology to compete. Maybe we could compete down the road, I don't know. However, for small scale or heavier contaminants, we can compete because I was speaking like to the farmers in say like desert areas. It's too cost prohibitive for them to do a small scale RO plant in the middle of the desert because there's generally no gas, and the small scale you don't get the economies of scale, whereas this we get very favorable economics even on a small scale. So this could be used for example, we're looking at solar desalinization, where we combine this system with the solar thermal, closed loop instead of a gas system. And in remote rural areas where they don't have energy or sustainable water, we could use a solar thermal, both to take well water or surface water, which more and more is becoming unsuitable for drinking, even sometimes unsuitable for agriculture. California, a lot of farmers can't use the aquifer water. Sometimes it's drying up, or sometimes the salinity and other contaminants are getting too high. So take that water, run it through a solar, and in that situation, we don't have to compete against RO, because unless there's heavy power or gas pipeline, it can't be economical to run at a large scale. Now, the bigger oil companies want a minimum of 10,000 barrels per day. Now we're looking at commercializing a 1,000 barrel per day or less system, which would fit in a trailer. Now that's our initial entry point in the marketplace, which are the smaller well sites. Once you get to 10,000 barrels per day or higher, and you're talking 50 cents if they're lucky, could be over $1 per barrel current cost. You're not talking a technology demonstration, you're talking infrastructure project. And that's really what we're looking at 10,000 barrels per day or higher. So I think over time, this technology, through running them in parallel, which is the same thing that a large-scale RO plant does. Each reverse osmosis desalinization membrane does a small amount of water. But if you put enough of them in parallel, you could provide the water needs of a large city, which is what they're doing in several Middle East countries. So same thing here. So yes, I think eventually this technology will be used for large scale, and our hope is to do a pilot plant rollout of a 10,000 barrel per day plant next year. But even still, the costs are enormous. We're looking at a capital budget of around $1 million, an operating budget around $500,000. So the NSF is looking to give us matching grants, but we still need a major oil company to match it with the NSF. And I think we're going to get it, and it's going to get done. And I agree. That's our next generation of technology.
Thank you, Gary. That helps.
Excuse
Thank
me,
you.
I have a quick question if you don't mind.
Yes.
Initially, the question that I submitted with the chat had to do with the nature of the pre-treatment processes. And I did hear you mention electrocoagulation, but I was unaware of that when I wrote the question. Now, I wanted to know if the pre-treatment is more or less dictated by the composition of the original input water.
Yes, absolutely yes. So that is probably the number one factor. The second factor is, are we recycling the brine? So if we want to recycle the brine as a high value drilling mud, we're probably going to have to pre-treat unless the chemistry is very clean. It is possible to get very clean chemistry. It's rare where we won't have to pre-treat it and we can still recycle it. But if there's a certain amount of iron or other contaminants, or we're not getting a high enough density, the drillers are not going to want the brine. So yes, the number one factor is the quality of the produced water in. Probably the number two is, what do we want to do with the brine? If we want to just dispose of it, there's probably not as much of a need for pre-treatment. So in that situation, we go for a cheaper approach, no pre-treatment, just run it directly through the system. Now, and this is why I said I don't think any one solution is going to solve the problem.
And then just very quickly, what's the energy efficiency of, I was putting a little pen, I'm not an engineer, so, you know, but I figured it would probably take about a third of an MCF of gas of 1,000 BTU per cubic foot heat value to raise to 1,000 degrees Fahrenheit a barrel of water. And so yes, if that were 100% efficient, but of course then if it's not 100%, you're going to have more volume of gas to burn.
Yeah, actually we're not 100% efficient, but we're seeing better numbers than that. How's that possible? Is that our fin tubes properly insulated are over 90% efficient, so it's actually a very simple, efficient heat transfer system. But what we're not calculating in is also the energy recapture. So we're recapturing most of the energy through the pre-warmers and the condensation. So the energy recapture improves the economics. Also, when we did a simple calculation, it didn't make sense under the laws of thermodynamics that we were getting better results, even calculating the energy recapture, when we did a simple. So I didn't understand it either. So I actually spoke to a chemical engineer expert at Rice University and showed her the data and said, "What's going on? I believe this data is correct, but it's showing that." And she says, "All right, what's happening is you're having benefits through entropy through your system, and that's generally not considered in a thermodynamic calculation." So as I learned, it's not a very simple energy calculation.
No. Sorry.
Hello, this is Jerry Greenbaum.
Hey, Jerry.
Hi, Gary. So I've been quiet. Some of you folks know me, some of you don't. I've been a member of the group for a long time. I introduced Gary to the group. I'm helping him a little bit on this project. I wanted to talk to you guys about something that maybe you're not aware of regarding all this kinds of system.
Mm-hmm.
Number one, you know, we keep talking about injection wells. I don't know if you folks understand what it takes to permit an injection well under the EPA and under the state guidelines. That is a very laborious, expensive process, and it's, you know, it's time limited. It's reservoir specific. You have to, before you can do an injection well, you have to verify where you're going and what would you disturb in the way of other reservoirs, and you have to go below that. So the number of Class 1 injection wells under EPA is probably very small. So the people who have them probably not going to have them forever. You know what I mean?
Mm-hmm.
So I just wanted you to understand that concept.
Yes.
Some of my experiences been up there, like in Bowie, Texas. All these producers truck this water to a company's production system, where you see those tank batteries and everything, and then they will inject that. So that's a business to them too. You got to remember that. Or they're not going to build these tank batteries, because they're going to charge all these guys who are bringing the material in a lot of money, you know, just to store and process, and then they have to inject. So they're going to have to make money to recover all that. So it's very more complicated than you think. There's a whole business of that, and it's all site specific, depending, you know, to transport water or whatever. It's $1.50 a barrel, right?
Mm-hmm.
If you don't have an injection well, you got to go to the next guy, and maybe he's farther away, so you're gonna pay $2 or $3 a barrel to get rid of it.
Mm-hmm.
So you got to keep that in mind. So this is kind of a convoluted system here, how it works. So, you know, one thing is it's going to be very site specific. Like the well Gary showed you there is a small well, but some of the wells in the Permian Basin could be huge. I don't know if Gary wants to talk about that with one of the customers.
Yeah, so every well is different, every cost is different, so it makes it very difficult to do economic modeling on this, because obviously if you're lucky enough to have a disposal well that on site that only costs you 50 cents a barrel, that's much different economics than if you have to ship it off site, and you're probably looking at $1.50 or more by truck. So, and also pipelines are a different story, because pipelines are a huge capital cost up front, but once they're up and running, it's not as expensive. It's not that expensive to run, but it's still a cost. So, and then you got your maintenance costs. So, even among the oil companies, exactly how do they account for these? Now, as far as the number of disposal wells, they're going down, and the reason being is, like Jerry said, because the permitting's become very much difficult. A couple of years ago, the Texas Railroad Commission, which controlled the permits, they hired a seismologist to be on staff, and every disposal well, you have to have a report on the seismic risk and the risk of causing man-made earthquakes or seismic activity. So the majority of, from what I understand, the majority of rejections now used to be very rare that you would get rejected on a disposal well permit. Now it's becoming very common, and one of the most common reasons is you didn't properly consider, or you didn't consider at all, the seismic risk. So this is going to, and most people are saying that the seismic risk is going to increase over time. So this is something that the industry's been dealing with, and it's becoming a bigger and bigger concern.
Hey, Gary, this is Subhash again. So just a follow-up question. What's the volume of produced water in an unconventional well, hydraulically fracked unconventional well, modern wells, versus, say, a mature water flood conventional well, which has a high water to oil ratio? Now, where is more water have to be produced and hauled?
All right, I'll give you the cop-out answer. It depends. Every well is different, which is really true. In fact, I had a professor who said, if you ever ask the question, say it depends, because there's always some variable that you always be right. So both conventional wells and unconventional wells, there's variations all over the map. Generally speaking, a conventional well has a very small amount of water initially, and that goes up over time. Now, if you want to prove me wrong, you can find plenty of examples where I'm wrong. I'm speaking in generalities. Whereas generally a fracking well has higher water cut initially, and then the water cut goes down over time. So that is generally how the wells operate. Anyone who's been in this industry long enough will tell you every basin, every well site is different. So, you could very well easily have a unconventional well that has a lot more water than a conventional well. And, so that's why it depends. One of the things we looked at on this technology is by having a scalable modular approach, we can increase or decrease the water throughput based on the needs by adding additional thermal distillation units. So if over time you need more, we can add more, either additional trailers or containers, or if we need less, we can remove some over time. So probably the best thing we could do is offer flexibility for the situation. So, sorry I couldn't give you a clear-cut answer, but in reality,
that's
there is
okay.
no clear-cut
That's
answer.
okay. What I was thinking is, the oil prices are down, and maybe, who knows how long they'll stay in this range. And when I agreed with you that the produced water cost, handling produced water cost, is a significant portion of the, operating cost. And I especially remember from my Permian days when we were operating wells with water to oil ratio of 10 to 1, 20 to 1, even 50 to 1. The water oil ratios were getting high. And the limiting factor to operate those wells happened to be the water handling cost at that time. Yes. So now I'm looking at new wells, in unconventional wells. I've not worked with them enough, but I know that fracking and all that would require water volumes. But I'm just trying to get a feel for what's the comparison, and at what point will this challenge the economics of oil production overall?
So we can't challenge the economics because oil production is such a difficult business right now that if we make the economics worse, even if we provide an environmental benefit, it's not going to work. So really, we have to save them money. Now, you're right. The number one factor in determining the economics of a well is your water cut and how costly it is to dispose of that water. In fact, there's a startup called Source Water. I think they're rebranding. I forgot their name. Where they're using, originally it was a marketplace to buy and sell water, but they've actually pivoted and they're using satellite imagery and very sophisticated AI and permitting to look at water, how much water is available, what's the cost, and selling that to the industry, because knowing how much the water is going to cost you, the fresh water, how much it's going to cost to dispose, where are the disposal wells, what's the price, what are the options, pipeline, trucks, also how many permits are being in the future. They even consider satellites, how many well pads are being cleared out, because typically 6 months before they drill, even before the permits start showing up on the records, that they'll clear out a space and get the well pad ready. They won't drill or do anything, but the backhoes will come in and clear out the vegetation and create a level pad for all the equipment to be installed. So on satellite, they can see that and they can know where the new areas where there's going to be drilling, and knowing whether or not there's enough infrastructure capacity to handle the water, because you don't have pipelines or disposal wells and you have to truck it a great distance. A well that was economical a year ago can no longer be economical. So now the variations of oil to water cut generally vary anywhere from a 1-to-1, if you're lucky, 1 barrel of water for 1 barrel of oil, to 1-to-20. And anything over 1-to-20, I was told, generally is not economical. And it even changes over time. I was at a well site where I asked what the water cut was, and he says, around 5-to-1. But you know how you tell? You see that number right there? That's the barrels that we produce today of water. That number there is the barrel of oils we produce. And I looked at it, and it was almost 20-to-1. I said, you realize it's 20-to-1. Looked at it and said, oh, something must have happened today, because it's normally not that high. So even in a production site, it varies from day to day. So just enormous variations, and we have to be prepared for all that.
Gary?
Yeah?
There was a question on seismicity, and you mentioned the Texas Railroad Commission has hired a seismologist on their team to study before they provide an approval for injection well drilling.
Yes.
You gave some examples of seismicity of different parts of the U.S., highest being in Oklahoma, the state of Oklahoma. And have you looked into it? Because Texas Railroad Commission has approved plenty of injection wells to be drilled across Texas state. It is less than the permit that were granted in the state of Oklahoma. But why there are high seismicities in the state of Oklahoma as opposed to Texas or other places? Have you looked into that? What is your answer to that?
The biggest issue was in Oklahoma, the faults were much closer to the where they're disposing the waters. So they were seeing much quicker and much more drastic earthquakes. So from what I am understanding is that in Texas, the good thing is the faults are further away from a lot of these production basins. Mm-hmm. However, what we're seeing is over time, the pressure from these injection wells actually can traverse quite a far distance, and eventually will start pressurizing these faults. And it's a known phenomenon that if you pressurize a fault, you're going to have increased seismic activity in earthquakes. Mm-hmm. And Texas hasn't seen the large-scale earthquakes that Oklahoma has, but the number and intensity has steadily increased to the point where the Railroad Commission is now spending millions of dollars monitoring it and understanding it. So you're right. You could still get a disposal permit, and there's quite a bit of it, but it's a concern, and most experts I talk to say the concern is going to increase over time.
Gary, let me just ask a question as a part of our comment. Are you saying this seismicity is due to fracking or associated with fracking or with production or with re-injection?
It depends on who you ask. The popular press always loves to blame fracking. Every expert I've spoken to says it's the disposal water, because fracking, part of the reason why fracking became so cheap and so effective is these frackers became very good at only fracking the reservoir that they need to. And they're not fracking fault zones. Generally speaking, a fault zone is not a hydrocarbon producing system, because the fault allows the oil and gas to escape. Now,
Yes.
No?
No, what I'm saying is there is these three phenomena can reduce seismicity, but the seismicity is different in scale and in location.
Yes.
That there is seismicity through fracking, seismicity through unbalanced production or high-speed production, and seismicity due to re-injection or disposal wells.
Yes.
And it all depends on the location of the well and the nearby fault systems.
Yeah.
So if you are away from those, you can still have seismicity, but it's a very small magnitude and less effective than if it's close to a fault system.
Yes.
And people try not to distinguish between these different scenarios.
Yes.
Seismicity associated with fracking versus seismicity associated with rapid production versus seismicity associated with the re-injection of the disposal fluids. Yeah. And that by itself, mixing all these three different types of seismicity confuse the issue and confuse, I don't know if in permitting for disposal well, there is a distinction between these all seismicity or just if all the seismicity is seismicity. It doesn't make sense to me.
So in the media, it's basically, they're always saying fracking. Now, the degree and the significance of seismic activity from fracking and rapid depletion,
yes,
can be detected, but is nowhere near the problem of these disposal wells. And the volumes and the amounts are so why it theoretically is an issue, almost everyone I heard agrees that the main seismic concern and the increase is from the volumes of disposal, not from rapid depletion and fracking. Although a lot of times the anti-oil and gas companies, you're right, critics don't make a distinction, and it's very easy to blame fracking because for some reason fracking has this evil buzzword that everyone hates, and from what I understand and from speaking to the seismic experts, that fracking is not the problem.
You know, the
I agree with you.
The injection in application for injection well or water disposal well that Jerry alluded to earlier, those injection well permits require you to specify the pressure gradients, require you the radius of investigation, that sort of thing, what radius it will be affected, how close you are to the fault and all that. So if the state of Oklahoma did not, if they were lax in regulating those, then that could have played a role compared to, say, Texas Railroad Commission, for example.
Gary, I'll put 2 cents of mine following what Mamdouh has said. I think this seismicity can occur by all three means that he mentioned, but however, you have to separate them out. And one is the case is in Oklahoma, the faults are shallower, whereas in Texas, most of the faults are really deep-seated. So, and when they're doing this, even from fracturing, they had a seismicity. And this seismicity is because of the fact, these faults, when you're fracturing, if there is a shear fracture that happens, shear slippage, that is what causes your seismicity, not the compressional stresses or anything. On the other hand, when you're injecting a lot of disposal water back into the formation, injection wells and whatever it is, disposal wells, what you are doing, you are creating higher pore pressure. So what happens here, effective stress, which is the combination of the stress minus pore pressure, the effective stress goes up, reduces, sorry. And then that in turn can cause slippages. So
Yes.
it is fracturing, seismicity is caused by both this phenomenon. And the third one that he mentioned about rapid rate of production, that can cause as well, because that's why the pore pressure issue comes back again. And that could cause it, but I'm not sure percentage-wise of these three, which one has the highest effect. And that's why when you talk about environmentalist, I think that's why environment to some extent, I think they're right in fracturing. If you do fracture close to a fault zone, as it is done, as has been done in Oklahoma State, and it happened from that as well.
Another thing, especially in Oklahoma, as you said, they use the the zone, the natural fractures as a high permeability zone where they can expand the disposal away from the well. So again, with that, they generate a fluid slippage on these fractures, causing local seismicity along the fractures themselves due to the movement of the hanging wall on the footwall. And that's due to lubrication with the injection fluid. So again, I am saying that the injection related seismicity and activation along the fracture zone need to be a category by itself, different than any other seismicity, because the other seismicities are much smaller and much safer than what the reactivation along these fracture zones.
Yeah. Actually, I'm not an expert in this area, but if you wanted to get an expert, there's a woman named Laura Kappa, and she does consulting for a lot of the big oil companies and does a report on seismicity, and she has a lot of interesting discoveries. One of them was it's not just increasing pressure, but a decrease in pressure can actually cause seismic activity too, which is interesting.
Yes.
No, but that's the idea I was saying about lubrication of the fluids along the fracture zone. It does not only increase the pore pressure, but any disturbance along this fracture zone, allowing the two blocks to move against each other, the friction that's causing or resulting from that is the cause of the seismicity. And as Salim said it, this will happen most effectively in shallow zones, not in deep-seated faults. So again, the idea of reactivation and seismicity related to injection need to be really, we need to be careful about that compared to other types of seismicity associated with the production or fracking.
I guess it's possible to have a fracture trap type system in a hydrocarbon producing zone, but that's probably not very common. So very rarely do you have hydrocarbon systems directly on the fault, because like I said, a fault usually causes a migration of hydrocarbons because it destroys the permeability and the cap. So usually the reservoir is offset by a cap rock. some distance from the fault. So fracking, you're only going to frack the hydrocarbon, and the reduction is only going to be a hydrocarbon zone. So that's why I think it's possible to have a frac job or a rapid reduction cause a fault slippage, but in practicality, it's not very common.
Gary, when you talked about high pore pressure, actually a high pressure is not what causes the slippage, is more related to the stress. So high pore pressure will reduce your effective stress, because effective stress is really stress minus pore pressure. The higher the pore pressure, your effective stress is going to go down, and that is going to cause the slippage. So that's
that makes sense. Again, I'm not an expert in here. I know enough just to be dangerous on the topic. The person probably you want to talk to on theory is probably Laura Kappa.
What's the name?
Laura Kappa.
Well, you and I talk. You can text it to us.
Yeah. She
or in the chat session you can type the name.
Yeah, she'll be much more. She does a lot of talks at like the Produced Water Society and other water events, so she's well known in the industry.
You have heard the name Mark Zoback, Stanford University professor on geomechanics?
Yes.
No.
He's an expert in this area as well, and he has a book as well on this.
University of Stanford?
Yeah, yes. Stanford. Yes. Yeah, Mark Zoback.
Okay.
His book is called, I have it in my shelf, Reservoir Geomechanics, I believe.
Okay. So,
it's published book.
On the theory side and Mark Zoberg or
Zoback.
Laura Kappa would be the much better experts on this.
Okay. Yeah, please send us the name later on, or you can type it in a chat session. Here is a question from to Jerry. Jerry, you are still there?
Yes, I'm here.
Can you do me a favor? Can you type your last name in the chat session, either to me or to Jeffrey Woodham?
Okay.
Please. Thanks. I have another question for you.
When I punched the chat, it said Jeffrey Woodham. Who is that?
Yeah, Jeffrey Woodham. Or you can send it to me, then I'll in turn send it to him.
Oh. All right.
I have another question for Gary. Gary, you mentioned that the produced water that you are recovering, it has H2S and arsenic. Do you know arsenic, is that from an arsenopyrite layer in the subsurface where it is coming from?
Honestly, I don't have any clue. Arsenic is a naturally occurring compound, so it's in various degrees. Certain areas have higher, certain areas have lower. H2S is a problem in some wells. It can be treated with pre-treatment. Again, if it's not economical to pre-treat it, there's plenty of wells that have little or no H2S. So it really, again, depends on the well site.
My question then comes in, do you see arsenic and sulfur is produced mainly from wherever you get the arsenic, from the same place you also are getting sulfur? Have you noticed it?
I'm not sure.
Okay, pay attention to it. If it is, that means it is coming out from arsenopyrite. Pyrite itself is a sulfide.
Yeah.
What is it?
FeS4,
Fe2SO3 or something like that.
Again, that type of question would probably be better posed to the geochemist, because I probably looked at maybe a dozen produced water samples that we've run. So I don't have a big enough sample size to even take an educated guess.
because I used to do a study on environmental issues back in West Bengal of India, as well as the northern part of Bangladesh. There is a huge layer of arsenic layer. There's a lot of people who are drinking water, potable water, they're getting skin cancer out of it. So that's why it came to my mind, how many of those arsenic rich layers exist in United States, in the places where we're producing produced waters and all that. So anyway, are there other questions to Gary at the moment?
Hey, this is Jerry Greenbaum again. I'm sorry. What I was going to tell you, if you go out to the Permian Basin and you get produced water, that's the worst water in the whole world. It's that black, stinky water. You ever looked at it? And that's all reservoir specific. You got to go down there, and when that water comes up, you're getting everything from drilling mud to whatever else they stuck in that well, and that all comes out. So every well is different. But the point of it is that traditionally in the Permian Basin, they brought that water up and put it into an injection well. They never would treat it, because what's happening out there in a lot of those fields, there's also water floods that are going on. You know that? So they have a big mess out there because that produced water is causing a lot of problems with the water flooding, right?
So
water flood used to be used as a secondary recovery process in Permian Basin some time ago, before they started
I know, but
producing from unconventional.
A lot of times they're still doing it in some of those fields.
Some of the fields, yes. Some of the zones, yes. That's right. You were right. Yeah.
So.
Okay. Yeah.
So if you get the water analysis of the produced water, you're going to see it's worse than seawater. You know, seawater is 20,000 parts per million. This stuff could be everything in the world that went on out there. So rather than, most companies don't want to mess with that. That's why they injection well it. But the thing is, the injection wells, I still don't hear this from you. If you get the EPA guidance document on permitting a Class 1 injection well, there's a lot more that goes on than what we're talking about here. And when they do a well like that, you have a vertical from the ground all the way down, and all the injection water is way below any producing section. You know that? They said it came from the ground, put it back in the ground, but don't affect any of the oil producing reservoir part of that. So some of those wells, would have 12 or 1,500 pounds of pressure from the injection pumps, which means it's pretty deep. And so I don't think you're going to see much of the seismic from that. But and I'm not sure that the Railroad Commission has total responsibility for injection well permits.
I think the EPA sets the guidelines, but
no, the EPA is, you have a Class 1 injection well, period.
Yeah.
That's the EPA controls that. But as part of the process for permitting that, you also have a state agency that looks at it too. So, that's an expensive process. It's like any other environmental permit. So it's very costly. Just paper to get the permits.
Jerry, what is the Class 1 injection well? What do you mean? What is that?
That is a hazardous waste well, produced water type products. There's different classes of injection wells. Class 1 is the worst case.
Really? And EPA approves that?
Yeah, EPA is the main regulatory body.
Yes, I know. Yeah. Okay.
So,
And you know, that cost is never considered when you're doing this kind of work, you know, like what Gary's trying to do.
mhm. So, Gary, you said one thing is that in Marcellus, to transport the wastewater or produced water is about $8 per barrel. How do they make money?
They have a very hard time. So it's not always $8. It could be between $4 and $8 a barrel. So I think one of the ways is that they don't have as much water cut, but probably a lot of wells are uneconomical because of the water.
Uneconomical for what?
Because if they have too much water. So if you could reduce the water costs, you could probably increase the number of wells that are economical.
I see. Okay.
But it's a serious problem. At one point, the Marcellus was one of the most important production basins in America, and
yes,
you know, its importance has decreased because of probably partially because of the disposal problem.
I see.
Hey, Gary.
Yeah.
Also, most of the Marcellus stuff is gas production. It's very little oil.
Little oil, yeah. That's right.
So there's probably less associated water.
Associated water, probably, yeah. That's right.
Yeah. Although the Marcellus, you're right. The Marcellus is mostly gas, but there's a lot of gas condensate. The liquid gas.
Yeah.
Natural liquid gas. So I know that some chemical plants are being placed out there to use the the NGLs as a base stock.
NGL, yeah.
Well, that would come out of that first separator, you know, it'd be part of the gas stream, and then they would process it and condense it, you know.
Yeah.
So that has nothing to do with your subject.
Yeah.
Gary, you talked about aromatics as well. And what is a VOC or VOL or something, a term you use? What is that?
Volatile organic carbon, or.
Oh, I see. So you have a hard time to separate out aromatic components. Is that correct?
Well, our system won't separate it out. Actually, what it does is it does take it out of solution, and over time it will evaporate if you let it sit long enough. I mean, it will just vent off. But that's one of the things. That's probably one of the few things we can't handle. But the good news is there's other technologies for that.
Okay. Thanks a lot. Yeah. Well, do we have other questions for Gary, or any comments? Hello?
Yeah, I'd love to follow up if anyone wants to email me or call me, figure out ways to help each other. I'd love to continue the discussion. This afternoon I'm going to be really busy, but appreciate listening to me. I know I didn't think it would be this hard, but I'm actually tired after talking for 2.5 hours almost.
Yeah.
Thank you very much. It was a
2.5 hours. Yeah.
presentation. And
thanks a lot. We all appreciate you coming over and making the presentation to all of us. It's a topic of great interest to all of us, and that is the reason I thought it'll really fly, and it will probably show generate a lot of interest.
Okay, awesome.
Thank you, Gary. Learned a lot.
Thank you very much, Gary.
Thanks, Gary.
Great
job. Thanks much.
Thank you.
All right.
And do you guys want to go out in a breakout session?